dynamic systems. And as soon as you say that, it's starting to go in the direction of resolving the paradox. Because remember, the problem was you throw something into the black hole, and where did the information go? And if we're now saying that the black hole actually has a large number of hidden degrees of freedom that aren't manifest in general relativity, but they're somehow there, then you immediately say, okay, great, well, that's where the information is of how I made the black hole. It's in those hidden degrees of freedom. And so somehow, if we can just get it out, then we can learn, we can try to make black holes consistent with quantum mechanics.
And before you go on, just hold that point for one second. It might be worthwhile for the audience to recognize, because you made reference to Jacob Bekenstein earlier, who's also vital to this, who's advisor with John Wheeler at Princeton. And Wheeler was one of the people who really caused the renaissance of thinking about black holes in the late 60s and 70s. And he worried that if he took, he was a very genteel man. I don't know if you ever met him personally, but he was wonderful. He said, if I have a cup of hot tea and I throw it into a black hole, I seem to have gotten rid of all the disorder, all the entropy of the hot cup of tea. And how could that be? I seem to have violated the second law of thermodynamics. And he gave this puzzle to Jacob Bekenstein, who then realized what you just described. You throw that cup of tea in, the black hole changes. Its surface area grows a little bit, and that surface area is indeed capturing the entropy, the hidden degrees of freedom of a black hole itself.
That's right, exactly. Yeah, and that paper of Bekenstein is really wonderful to read. In some sense, it's more modern than Hawking's paper. Hawking's paper is in some sense better because he computed the number. He computed that the entropy is the area divided by 4 times Newton's constant. So there's a 4 there that's important to get right. And Hawking also gave the mechanism whereby black holes radiate. But this earlier paper of Bekenstein is really nice because it really makes nicely this case that there are really these hidden degrees of freedom. Now, to get to 't Hooft and Susskind, so they were trying to understand.
Let's go, Susskind! Yeah, we made it. Yeah, let's go. Right. All right, you better not say anything fucking angry. I can't retract my email.
Understand this formula for the entropy of a black hole. And so let me again say the formula. It says that the entropy of the black hole, the number of degrees of freedom of the black hole, is equal to its surface area divided by 4 times Newton's constant.
That's right. Okay.
There are various other constants there, like the speed of light and h bar and Boltzmann's constant, but we're adults here, so those are all 1.
It's beautiful.
We'll choose our units so they're 1, so just so the audience is clear.
We work in units where they're 1. Yeah.
It's beautiful.
And so before you get to the formula
and
how they think about it, it might be also useful if you agree. If we describe this puzzle that things fall into a black hole, it radiates, their information seems to be lost because the radiation seems not to carry the information regarding what fell in. But if you're looking at the black hole from far away, which after all is where you were measuring that radiation that came out, you mentioned at infinity, just far away. Can you describe for us what you see when things fall into a black hole?
Yeah, well, really not. Well, so I mean, for real black holes, that's a complicated question. There's an accretion disk, et cetera. Okay, but for an isolated black hole in the universe all by itself, the answer is you don't see too much. The object, say it's an astronaut, is falling towards the horizon, and as they fall towards the horizon, they start to look dimmer and dimmer,
right?
Due to the gravitational redshift, and
that's
also
right. Or it might be blue as you get closer, or something.
Say the astronaut is holding a flashlight and pointing it at me just to make sure that I can see them.
Or whatever it is.